Our first speaker is Ludovic Plante, and he will tell us about a method to derive classical gravity from scattering amplitudes.
Yes, thank you, Radu. So thank you for the organizers for the invitation, and I will speak, as you said, on a method we have been developing to derive classical gravity from scattering amplitudes. So we have been working with Emil Björnborg, Paul Damgaard, and Pierre Vanov on that in a series of 4 papers in this year. So I will not read this, but I will just maybe say a little disclaimer here to say that I will not speak today about computing integrals, but more on how we can build classical integrands to extract classical gravity from scattering amplitudes. So first on motivation. So as you all know, general relativity is a beautiful and efficient theory to describe gravity. And it has been confirmed that high orders of precision, especially in the detection of gravitational waves emitted during the merging of binaries. So as we develop gravitational observations, we have a growing need to improve the prediction and the computation of gravitational waveforms that are observed by LIGO and Virgo, for example. So there are several ways to compute gravitational observables, but one way is to compute scattering amplitudes in quantum field theory and to extract the classical quantities from these scattering amplitudes. So at first sight, you can say that you could think that the scattering amplitudes are not the most efficient way to compute classical observables because scattering amplitudes are quantum quantities, and you have to compute them and take h bar to 0, and you have some issues to extract the classical pieces from that. But in fact, we can leverage all sorts of methods developed in QFT for many years now, as unitarity and double copy, to improve the computations and make scattering amplitudes an efficient method to compute classical quantities. And in fact, now the scattering amplitudes methods start to challenge some more standard methods as methods, for example, using PN computation or other methods. And for scattering amplitudes, I think the way of efficiency is first to understand where the classical terms are hiding in the scattering amplitudes. So the scattering amplitudes are naturally derived as a perturbative loop expansion. So you expand your amplitude in loops which correspond to an expansion in the Compline constant. So here it's a G. So it's a post-Minkowskian expansion. So you expand here your scattering amplitudes as a sum over the loops. And an issue when you have your scattering amplitude is to link your scattering amplitudes with the observables. So for example, to link the amplitudes with the scattering angle. And you have several methods to do that, like the iconal or the EFT matching. But here I will say some words about the method we have been developing on that also. So the question I want to solve during this talk is first how we can compute scattering amplitudes for Einstein theory. Second, where are hiding the classical terms in the scattering amplitudes and how we can efficiently extract the classical terms in the scattering amplitudes. And third, how we can relate the scattering amplitudes to the observables as the scattering angles so that the computation is useful to experiment. So some definition first. So we consider a 4-point scattering amplitudes with P1 and P1 prime being scalars of mass M1 and P2 and P2 prime scalars of mass M2. And you define your Mendelssohn variables. So S is mainly the square of energy, and sigma is the product of P1 and P2. T is the square of the momentum transfer. And U, I mean, is not independent of S and T, as you know. So S and T are the 2 independent Mendelssohn variables. Then another ingredient you use to find the classical pieces in the scattering amplitudes is the soft expansion. So you do an expansion in small momentum transfer, which corresponds to a Laurent expansion in h bar. So you can build a classification of the different correction in the order of classicality. And in fact, at L loop, you want to find this term, which is 1 over h bar and 1 over q at the power 2 minus d minus 3L, which is the classical term. So first, I want to say a word about how we use GR as an EFT and how we compute the amplitude in GR. So it is known for a long time now that you can derive the Feynman rules and amplitudes from Einstein-Hilbert Lagrangian. So you take the Einstein-Hilbert Lagrangian and you expand G, the metric around the Minkowski metric, and H is your graviton field. And you can build like that vertices, Feynman diagrams, and amplitudes. Only problems being that you have an infinite number of self-interactions of gravitons, and you have a lot of UV divergences, and you have a normalizable theory. So what you do is, in fact, we are interested in the long distance contributions of gravity. So we can use gravity as an effective field theory, building this Lagrangian, and this piece is being correction to Einstein theory from UV completion. And doing that, we can treat gravity as an effective field theory and avoid all usual ultraviolet complication in quantizing gravity. So this is a good setup for studying the black hole binary majors. As I said, we are looking for soft expansion of your scattering amplitude. So typically you will build this kind of Feynman diagrams, and you expand them in h bar, in h bar or q square. So very generally, when you take an L loop amplitude, it has this expansion in h bar and q, and the classical term, as I said here, correspond to the when r equal L minus 2, and you see that in the tree at tree level, when L equals 0, it corresponds to exactly to the term to the leading term. But at each loop order, you see that you have more and more superclassical terms that appear when r equal minus 2, minus 1, 0, etc. until L minus 2, that hide a bit more at each order the classical term in the soft expansion. So these superclassical terms have to be cancelled. So for example, in the iconal, you cancel them by exponentiating. But this raises a question of computing only and directly the classical r equal L minus 2 term at the level of the integrand, so that you don't have to compute them in the end. To do that, we do an exponentiation of the S matrix. So you know that the S matrix, the S operator can be written like 1 plus I over h bar t, when t is a transition operator and which is directly linked to scattering amplitudes. But you can also use another representation that is, you can write S as an exponential of another operator that we call n. And as S is unitary, you know that n is Hermitian. So it means that the eigenvalues of n are real. So we find that n is a more natural representation to compute classical quantities. And doing the exponentiation, so you do it at the operator level. So when you are considering states, you have to insert between your n the complete set of states and sandwich the n between the states. So just to show what it looks like, you can show a few examples. So at one loop, you see that you can exponentiate your formula here and get that n1 is equal to m1 minus a contribution, which is a product of m0 and a square of m0. And here you have a unitarity cost that corresponds to the complete set of states that I have here. And okay, you can ask why is it helpful? So as I told you before, m1 at one loop is in the soft expansion as 1 over q square. And the classical term is at 1 over q. So you have a super classical term to cancel in m1. But in fact, if you count here the order of q, M0 is of order 1 over q square here also, so it's 1 over q4. Each massive propagator will be of order 1 over q, and you have an integration on that, which brings the q power 4. So at the end, this quantity is also a 1 over q square. So in fact, the super classical term here will be exactly cancelled by this cut contribution, and N1 will be directly classical of order 1 over h bar. At two loop, it works the same way. So at two loop, you have an iteration which is the cube of the tree, and you have a contribution which is the product of a tree and a one loop amplitude. And you have also a new type of contribution, because here I said that when you exponentiate and you insert your complete set of states, you can insert scalars, obviously, but you can also insert gravitons, and you can start to insert them at two loop. So when you do that, you generate an imaginary piece that is in fact cancelling the radiation reaction, the divergent 1 over epsilon radiation reaction imaginary piece in M2. So at the end, we check that doing that.
Sorry. So what's the meaning of dashed line? It's a unitary cut.
Sorry, can we wait the end of the talk for question, or do we?
Yeah,
I mean,
better leave it for the end.
It depends. If the answer
Okay.
is very quick, then you may answer. Otherwise, we should leave it for the end.
I don't know.
Okay.
I didn't understand the question. Can we maybe we can ask at the end?
Okay. Yeah, let's leave it for the end then.
Okay. So at two loop, doing that, you find that N2 is a classical quantity and a real quantity, and at one and two loop, you can show that if you take the derivative of n regarding the angular momentum, you get directly the scattering angle. So another thing that we use to compute scattering amplitudes with modern methods is we generalize the integrants with generalized unitarity cuts, meaning that you build your integrand using cut, so that you have to just multiply on shell 3 scattering amplitudes. So the strategic pieces to compute is 3 amplitudes where you have 2 scalars that are emitting, let's say, n gravitons, so that afterwards you can multiply them and compute your integrands. I have to say here that you have other cuts, like I think Shashen showed in his talk, that you have to consider, especially for radiation reaction, but it will follow the same kind of ideas. You can, the main quantities you have to compute is really this kind of scattering amplitude 3 when you have 2 scalars and gravitons. So the idea is to say, okay, what can we do with the trees, and can we write the trees in a specific way so that we can use our exponentiation and cancel the superclassical terms at the level of the integrand. So the idea is to consider a tree amplitude where you have 2 scalars that emit n gravitons, and you pick a specific graviton momenta like Li here, and you express it with momentum conservation in terms of Q, momentum transfer, and the other gravitons momenta. Doing that, you can classify your propagators in 2 kinds. So you have the propagators that have Li in them. So you express Li like this. So your propagator is typically like P1 minus some momenta. So if you expand it, you expand the square, you get 2 P1 dot some momenta minus I epsilon. And if you don't have Li in your propagators, you get P1 plus some gravitons momenta. So you get typically 2 P1 dot some graviton momenta plus I epsilon. So you see here that the I epsilon prescription seems different considering P1 dot L minus I epsilon or P1 dot L plus I epsilon. So the idea is that you can use a relation that tells you that 1 over x minus I epsilon is equal to a delta function plus the opposite prescription, to flip some of the I epsilon to define m plus and m minus, where m plus is the amplitude where you have put all these P1 here, minus I epsilon to plus I epsilon, and the opposite for M minus. So all these kind of propagators, you put them from plus I epsilon to minus. So at 4 point, for example, you can consider your 4-point trees, and you do the momenta you pick is L2, for example. So you express L2 like minus L3 minus Q. So doing that, you can show that you will flip this propagator P1 plus L2 square minus M1 square, because as I say here, we have to flip this one. And you will have a remainder, which is M plus. And when you do that, you know that you will get the delta function piece, which is here. And you know from the factorization theorem that in front of the delta function, in fact, you have two on-shell 3-point amplitudes. So at the end, you get M2 that is equal to a delta function times a product of 3-point amplitudes plus the quantity we call M plus. And you can generalize this identity at L plus 1 point. So if I emit L plus 1 gravitons, I will get a first contribution which has L delta function, a second contribution that has L minus 1 delta function, etc., until I have 1 delta function, and a remainder piece that is just an M plus, where I have put all the minus I epsilon propagators to plus I epsilon. So the question now you can ask is, okay, why is it useful? So it is useful when you consider the soft expansion. So for example, at 4 points, let's stay with this example. You take your 4-point amplitude and you expand it in Q. So L, the gravitons momenta behaves like Q, and you can expand your 3 amplitudes like this, where the leading piece is 1 over Q times delta function, and you have the second piece which is Q power 0. Now, when you compute plus, in fact, here it's like your delta function is just 1 over P dot L2 minus I epsilon minus 1 over P1 dot L2 plus I epsilon. So when you consider L plus, you will have turned your minus I epsilon to plus, so the delta function disappears, and you stay only with this piece. So it means that M plus is of order Q power 0. And in fact, this behavior can be generalized. So typically, the soft theorem tells you that if you have an amplitude with 2 scalars on L plus 1 gravitons, it will be of soft order 1 over Q power L. But on the opposite, an M plus or M minus amplitude will be only, and for all number of gravitons, only of order Q power 0. So I have to say that it seems that you can express this M plus of order Q power 0 as just a combination of leading soft Yang-Mills amplitude. So it seems that this flipped amplitude has some nice universality properties. So now the question is still, okay, why is it useful to build classical integrons? So the answer is that, in fact, if you consider an L loop integrand, and you consider just the L plus 1 cut, meaning that I have two scalars on the left that emit L plus 1 gravitons, and 2 scalars on the right that emit L plus 1 gravitons, and I cut it. So I can expand each 3 amplitudes on each side in the way I just showed, so that I can expand it like this, where I have, let's say here, K delta function, and a certain number of M plus amplitude, and another number of M minus amplitude. So now what about the soft counting of this integrand? So I know that M plus and M minus are of order Q power 0. I know that this delta function are of order, each is of order 1 over Q. The momentum, the loop momentum is of order Q. Same for here in the graviton propagator. So at the end, I get this soft counting, which goes from K equals 0 to 2L, depending on the number of the delta function. So now you can classify your H bar order or Q order. You see that if the number of the delta function is less than the loop order, then the pieces are quantum because you are or for the h power 0, h power 1, etc. So if I have more delta function than the number of loops, you have pieces that are super classical, and you will cancel them in the exponentiation because I will show an example at one loop just after. And in fact, if you have if the number of delta function is equal to the loop order, this is where the classical pieces are. Just you have to consider only connected parts because the others will not contribute. I can answer a question if there is on this point. So now you know that the classical integrands are built from pieces that have only k equal L delta function. Maybe to show what it means, I will show the one loop example. So at one loop,
10 minutes left, including the questions.
Okay, so at one loop, you consider two gravitons cut, and you consider three amplitudes on the left and on the right, and you expand them as the way I just showed. So you have one piece with a delta function and the plus amplitude or a minus here. So the first piece you have to consider is this, where you multiply this piece with this piece. And in fact, you see immediately that it will be exactly canceled by this iteration that we had from the exponentiation of the S matrix. So this piece will not contribute to N1. The other piece is this one, and there is a similar diagonal piece here that has only one delta function, and that will be exactly the piece contributing to N1. So maybe I don't have so much time, so I will say something, a bit of things about the problem. So we applied the method to compute the problem of for loop. So in the problem, you know that the relevant classical integrand is only this piece. When all the delta functions are put on the left side, for example, if M1 is bigger than M2, and you have to compute this piece where you have expanded the piece on the left, and you have only M minus on the right. And so you can compute the three amplitudes using double copy from Young-Mills amplitudes. So this is what we did up to 7 points. So you compute the right three amplitudes that emits 2, 3, 4, and 5 gravitons. So you have up to 7 points. And then you multiply them. And then you write it as an integrand and you integrate them. And the good thing with the problem is that you have only one master integral at each order, which is just the triangle master integral. And you can compute n up to the for loop order. And we get a match with the computation from the geodesic motion in Schwarzschild metric. So now, as a conclusion, I would say that, so we have developed a method to extract classical physics from scattering amplitudes. The general idea is to generate unitarity cuts at the three amplitudes level so that we can avoid superclassical terms, but at the integrand level. So we don't have to compute them and subtract them, but we can really cancel them at the integrand level and compute directly classical integrands. The other advantage of the method is that it works both in the conservative and the radiation sectors. And when you have delta function, you can decrease the dimension of the integral so that the basis of integrals is a little bit simpler. I mean, it's not much simpler, but it's a bit simpler. And you have to compute less integrals than in a general formalism. Then for the next step, I just want to say that there is a lot of things to investigate, like the universality properties of the plus and minus amplitudes I just tell you, the spin property, higher loop computation, high energy scattering, or maybe some result in problem some things like that. But I think there's a lot of things to be investigated. So thank you for your attention, and I will be happy to answer questions.
Thank you very much for a very clear talk. Are there any questions for Ludovic?
Sorry, how can you guarantee that the integrand constructed by this way is gauging invariant?
Is what?
Gauging invariant.
Can you repeat the question?
I mean, how can you get guarantee the integrand constructed in this way is gauging invariant? If you calculate the gravity scattering process.
You mean gauge invariance, if I understand?
Yeah.
I would say I would say all quantities here are gauge invariant, because I don't know where we could break gauge invariance.
More questions? Perhaps I can.
Sorry, maybe can I ask a quick question?
Please go ahead.
So these velocity cuts, like, do you see is there any way this can break down in higher orders, or you think this is now proven to all orders that you can get the classical quantity to even higher orders from this approach? Or would be is there any kind of trickiness that you might be missing something at higher orders?
I don't know. So in the probe, we proved that it works up to for loop. Now general. Sorry?
For general masses.
You mean general in what sense?
Going beyond the probe limit.
Okay. Yeah. I would say. I mean, we will try, and maybe we don't have a general theorem that it's working at all loop order, but for the moment it works up to 2 loop. So we'll see, but we don't have a general theorem that say that it will work, but I think it will. But yeah.
Maybe. Oh, do we have time for one?
Yeah, there is time for more questions. Yes.
So just to follow up, even at 2 loops, do you have an argument for why it works, which doesn't rely on comparing with a known answer?
What do you mean? I mean, we did an independent computation, not relying on any existing answer.
But the fact that dropping these pieces and that taking the logarithm this way works with radiation, is there a more general argument, or is it just, yeah, that's my question.
Yes, I think at all loop order you will have this kind of subtraction that will cancel the pieces that you have to cancel. I mean, so at 2 loop we showed that we cancel the 1 over h bar square, the 1 over h bar, and then you have this piece which cancel the imaginary piece that is in M2. So
I'm not worried about iteration pieces, but I'm worried about h bar over h bar. The fact that you have terms which can interfere with classical and quantum. So
yes, okay. So I think it's linked to the what I said here. So here you see, for example, you can have some diagrams like here that are a bit like this, with a tree here where you exchange one gravitons, and here a bubble, which is what we call a box bubble integral. But you see that this kind of pieces, they have, so at 2 loop you expect 2 velocity cuts, right? So here it's the case, for example, but this is cancelled in matching. So these pieces that are h bar over h bar, that seems to be a mix of a superclassical and a quantum, for example, like this box bubble, it is also cancelled in the matching.
Okay, thanks.
Donald.
Yeah,
the question is short.
Yes, well, it's more of a comment. So yeah, I think it was Julio who's looking there. It's a little hard to know, but there is, I think, another point of view on these, these constellations that Ludovic is talking about, which I'll talk about a little bit tomorrow. So they're all cancellations that are necessary for uncertainty to vanish. They're zero variance relations. So I think there actually is a firm reason to understand why all of these things have to happen, and they do have to happen like this. Anyway, that was it.
It's great. So we are dead on time. So let's thank Ludovic again.
Okay, thank you.
If there are further questions, please do use